Hello student, in my previous video we were talking about the solubility of gas in the liquid where solid is as gas and liquid is as solvent. Okay, and I discussed the Henry law and we solved the couple of numerical problem based on Henry's law to explain it to you. Now we move to the next topic, that is solutions of liquid in liquid. So the topic of this video is vapor process of the liquid solution. Do you know when we have liquid, liquid have some amount of volatility, or we would say some liquids are volatile or some are more volatile. Okay. Here in solutions of liquid in liquid, we were taking binary solutions. What do you mean by binary solutions? The solution containing the only two components, the components A and the component B. Okay, one component is act as a solute and the other is act as solvent, and these components are volatile solutions. What is a volatile solutions? The solution which get converted into the vapor after heating. Okay, such solutions or a liquid is called a volatile solution which convert into the vapor. Here I am taking the container in which take two components, liquid component, because I am talking about the solutions of liquid in liquid. So here I am taking the two liquid component. The first is named as A and the second is named as B component. Okay, when we will mix both, we get the mixtures or the solutions. Student, you can easily see these liquid get converted into the vapors. Okay, both liquid convert into the vapors, and these vapor molecules are randomly moved in these containers and do not escape the containers. They just randomly move in these containers. After some times or some temperatures, these molecules, these vapor molecules exert a pressures on the surface of liquid. Okay, on surface of liquids, and these pressures is called vapor pressures. The pressure exerted by the vapors on the surface of the liquid is called a vapor pressure. The pressure exerted by the vapor above the liquid surface in equilibrium with the liquid at a given temperature. Here these vapors get condensed and back to the water, back to the solutions, liquid, and these liquids evaporate and convert into the vapor. So you can also show that the equilibrium in evaporations and condensation. Evaporation and condensation. Evaporation and condensation. Here, why is called a vapor presses? Because these presses come from the liquid, means they go upward and later after condensation they go downward. There was a scientist who was named Raoults who gave a law for this particular case when we make solutions of liquid in liquid, and which is binary solutions and volatile component solutions. So our next topic is Raoult's law to explain above process. According to Raoult's law, partial vapor pressures of the component of the liquid which is volatile, okay, directly proportional to the mole fractions. When we compare both law, Henry's law and Raoult's law, we get the in Henry's law partial pressures of the gas which is directly proportional to mole fraction. But in Raoult's law, the partial vapor pressures of the liquid which is directly proportional to mole fractions. Here we can write like partial vapor pressures denoted as 1 directly proportional to mole fractions. In Henry law, partial pressure of the gas using, but in the Raoult's law, the partial vapor pressures of the liquid, because here this liquid is from the vapor. That's why here I am using the partial vapor pressures of the liquid. Okay. Let us assume the vapor pressures of first liquid as P1 and vapor pressure of second liquid or a component as P2. According to the Raoult's law, P1 equal to P0 1 multiplied by mole fractions 1. How according to Raoult's law, P1 directly proportional to X. After removing this proportionality constants, we get P0. Okay, this P0 is vapor pressure of pure liquid. What do you mean by vapor pressure of pure liquid? When both solutions are taken as separate, you can easily see when P1 and P2 taking as separately, this liquid which is I draw in blue pens which is P1, this P1 component form some vapors, and this is in pure form. There is no mixtures in this solutions, only one component are here. That's why we can say it's a pure liquid. When this pure liquid form a vapor pressure is called a vapor pressures of pure liquid. Similarly, in second solutions, and P2 knots is the vapor pressures of the pure liquid, and this is the partial pressure, and this P2 is the partial pressures, and P1 is the partial pressures of both liquids, P1 and P2. According to the Dalton's law of partial pressures, you know that the P total equal to P1 plus P2. P1 is what? P1 is the partial pressures of first component, and the P2 is the partial pressure of the second component. When we taking the value of P1 and value of P2 and both are putting in this formula, we get P total equal to P0 1 multiply x1 plus P0 2 multiply x2. X1 is already right as 1 minus x2. After multiplying P1 with 1 and x2, we get this. Here I am taking the x2 as common. So we have the formula for this is P total equal to P0 1 plus x2 P2 naught minus P1 naught. This is the formula to find the total pressures. For the calculations of partial pressure, we can use the P1 equal to x1 into P total and P2 is equal to x2 into P total. See the differences and similarities between the Raoult's law and Henry's law. Some points are here. First, both law applied to volatile component in solution. Okay, and second, both law state that the vapor pressure of one component is proportional to the mole fractions of that component. And the third is differences between both law is Raoult's law define the proportionality constant as the vapor pressure of the pure component, but the Henry's law define the proportionality constant at some experimentally determined value. Student, look at the phase diagram of Raoult's law. Here I am taking this, wait, like this, I draw this. At this point, here's mole fraction, and is the vapor pressure. Vapor pressure. Okay. At this point, the value of x1 is 1 greater compared to value of x2 is, okay. Here at this point, x1 is lower as compared to the value of x2. At this point, the value of first component, molarity, x1 is the molarity. The molarity of first component is greater in compared to second component, but here the molarity of first component is lower than the second component. Okay. When the value of mole fraction is greater, they form the greater vapor pressure, that is denoted as P0. I already told you P0 is the pure liquid, vapor pressure of pure liquid. Or you also know that the P is equals to x. If the more value of molar fractions, so we get the more vapor pressure. If the moles fraction is greater, we get the more vapor pressure. As we move right hand side, the value is decreases, so the vapor pressure is also decreases. You can see, okay. Here the value of mole fraction, second mole fractions of second component is more, so it form the more vapor pressure, can denote at P0 2. Okay. As it move here, you can see here the value of x2 is more, but as we move left hand side, the values decreases, so the vapor pressure is decreases. Okay. When we join both, we get P total. In between, we always get the total pressures, and this point we get the vapor pressures. This is the phase diagram for liquid in liquid solution. But what happened when we taking the solid in liquid solutions, solid as a solid particle and liquid as a solvent, in which only one liquid, for example there is a container containing the one liquid which is volatile, and this liquid form the vapor pressures. But when we added some solute particles like this, when we added some solute particles in the liquid, what happens? When we added some solid in this liquid, what happened? This liquid form less amount of vapor due to the solid. So for this phase diagrams, only one components are volatile, so taken as x1. Here more x1, the value of mole fraction is greater. Here they form the vapor pressures, and as we move here, this pressure decreases, this vapor pressure decreases. So here we get the linear because this is the solid in liquid solutions. Students, now we have complete these topic in my two videos, first, second, third, and the fourth one. So our next topic is ideal and non-ideal solutions. First of all, we have to know about the ideal solutions. What is the ideal solutions? Ideal solutions are those solutions which obey the Raoult's law. Ideal solutions are those solutions which obey the solutions which obey the Raoult's law exactly over the entire range of concentrations. It's called the ideal solutions. Those solutions which obey the Raoult's law. Raoult's law. What is the Raoult's law? The vapor pressures, partial vapor pressures of the liquid is equal to the pure partial pressure multiplied by mole fractions of first component. And the second point for the ideal solutions, what is the heat change on mixing is 0. It means enthalpy must be 0. What do you mean by enthalpy? Mixing of enthalpy? Enthalpy is 0 when in making the solutions there's two processes occur. The first is dissolutions and the second is crystallizations. Okay. If two things are mixed, there is not change in any heat. Okay. It means here neither gain nor a loss of heat in these solutions during the dissolutions and crystallization. That's why we can say delta H max equal to 0. For ideal solution, enthalpy mixings of enthalpy must be 0. And the third criteria for this, the volume change of mixing is 0. Okay. Here I am taking the solute and solvent, taking 1 liter solute and 1 liter solvent, which form the 2 liter solutions. Both sides of volumes are same. In adding this 2 liters and 2 liter, it means there is no change in the volumes during the mixings of these solutions. Okay, these criteria are the ideal solutions. These criteria followed by the solution is known as the ideal solutions. And the examples of ideal solutions: the first, solutions of benzene and toluene; second, n-hexane and n-heptane; third, chlorobenzene and bromobenzene; and fourth is bromoethane and iodoethane. Now, what is a non-ideal solution? The solution which do not obey the Raoult's law over the entire range of concentrations. P1 not equal to the P0 and X1, and P2 is not equal to the P0 and X2. Okay, this is the non-ideal solutions. What is the criteria for non-ideal solutions? They do not obey the Raoult's law first, and second is delta H mix is not equal to 0 and delta V mix not equal to 0. They do not obey the Raoult's law. So they show two type of deviation from the Raoult's law. The first, positive deviations from the Raoult's law, and the second, negative deviations from Raoult's law. What is the positive deviations? According to the Raoult's law, the solution must follow these path. Okay, those solutions which follow these path is called a ideal solution. But when the solutions does not follow these path is called non-ideal solutions. Here, when some solutions do not follow these path, they get increases, the pressure increases from this path. Okay, orange color pen. I'm using the orange color pen to showing the deviations. Here these pressures deviate from their original path, so they do not follow the Raoult's law, and it is a positive deviations from the Raoult's law. When these pressures decreases from their path, Raoult's law, so this is called a negative deviations. Second, the solutions of ethyl alcohol and cyclohexane. In this solution, when we see ethyl alcohol, here is the ethyl alcohol, these are the C2H5OH, this is ethyl alcohol, formula ethyl alcohol. When the molecules of ethyl alcohols form the bond with each others, and these bonds are hydrogen bonds, and you know that the hydrogen bond is a strong bond, so this is not easily break. Okay, that's why the escaping tendency of alcohol and cyclohexane from the solution is increases. When one solvent AABB or AB, this sort assume as ethyl alcohol, and this assume as the cyclohexane. There is a hydrogen bonding between them. When we mix both, they form the weaker bond between them, A and B. That's why they break easily, and so escaping tendency of alcohol and cyclohexane from the solution increases. That's why pressure is, they form the more vapor pressure. For example, AB force are less than the AA force and BB force. In A force form hydrogen bond, BB force form hydrogen bonds, but when they are mixed, they form the weak bond. That's why it easily break, and both components form more vapor. When more vapor and more pressure is exerted, that's why they deviate more from their path. Okay, but in the negative deviations, what happened? According to some examples, the solutions of acetones and chloroforms, after mixing both acetones, there is no hydrogen bonding, and chloroform, it has also no hydrogen bonds, but when both are mixed, they form the hydrogen bonding. When after mixing they form the hydrogen bonding, they do not easily break. That's why escaping tendency decreases. So when they do not break, so do not escape, that's why they do not form more vapors, and when no vapor, less vapor, so this pressure exerted by vapor is less. That's why this vapor pressure is exerted in less in compared to the Raoult's law original. Let's see some difference between the positive deviation and negative deviations. Vmix is positive, and Vhmix is also positive. Vhmix is negative, Vmix is negative. Example of positive deviation is ethyl alcohol and water. Second, solutions of acetone and benzene. Third, ethyl alcohol and cyclohexane. You can easily see the hydrogen bonding present in solutes or solvent, not in the solutions. But here acetones and chloroforms, and second is chloroform and nitric acid, and third is water and nitric acid. You can easily see there is no hydrogen bond, strong bonds in solute and solvent, but here is the strong bond. Due to strong bonding, they do not easily break, and that's why when these molecules not break, so do not form a separate vapor, which separate vapor pressure, that why the pressure decreases.